Hello everyone, welcome back to the Engineer's Insight. Again, I am Cabuñas. I am a civil engineer and I am also an engineering professor. And I'd like to welcome you all to a brand new series of the Engineer's Insight. This is the Board Exam 101, in which in this series I am going to help you on solving and familiarizing past board exam problems. I know guys that it has been so long na since my last upload, but I am still hoping that you keep on supporting me in creating more videos to help engineering students. Now, as what I have mentioned, this is a brand new series, and the first video that I am going to teach you is one of the most occurring topic in the board exam, and that is the projectile motion. Our first problem would be from the Civil Engineering Board exam in May 2009. So it says that a projectile is fixed at a certain angle to reach a maximum range with a velocity of 10 meters per second. So we are asked to compute the following. So the first, the time the projectile will reach the ground. Second, the maximum height reached by the projectile. And the last question is the distance traveled by the projectile. So the first thing we must do here is, of course, to draw the problem and state the given. So to better understand the problem, we have to make sure that we draw it properly. When we say projectile motion, this refers to an object being thrown at a certain angle, which means that the object will follow a curvilinear path like this one here on the figure. So as what you can see, this is our initial point of the object, okay? And this is the final point of the object. Let's say this is our point 2. So at point 1, we would have this initial velocity. The initial velocity here is, according to the problem, this is 10 meters per second. And since the object follows a curvilinear motion, that means the ball is thrown at a certain angle. So we have here would be our angle theta. But since the problem did not indicate a value of the angle, that means we would have to compute this one. But according to the problem, the angle should help the object to reach a maximum range, okay? And that maximum range would be achieved if the angle theta is equal to 45 degrees. This is from the derivation. So again, when the problem says maximum range, that always constitutes to an angle theta equal to 45 degrees. How does this theta becomes 45 degrees when we are referring to maximum range? Now, when we say maximum range, that is the maximum horizontal distance from the initial point to the final point. So this would be our range R. Okay? And of course, during the final point, we would also have this, we would also have the value of the time when the object hits the ground. Okay, so that would be the first question of this problem. So again, our first goal here is to derive theta equals to 45 degrees when we have this maximum horizontal distance. So now we have now we already know the formula when we are solving projectile motion, if you remember your physics. So the formula that we will be using here is the formula for the vertical distance. So the formula of y, as we all know, that is equal to y equals to the initial velocity times the time, okay? Then plus minus the 1/2 of the gravitational acceleration, that's g, then t squared. Now, since our velocity here is at a certain angle, that means we would have the horizontal and vertical component of the velocity. So therefore, we would have here, that is the velocity x, and we also have the vertical component of the velocity. Let's say that's our vy. Now to compute for vx, that is the velocity, the initial velocity, and that is the cosine of theta, correct? And vy here is the velocity sine of the angle theta. So in this case, since we are referring for the vertical height, y, that means we will be using here the vertical component of the initial velocity. So that means we would have y equals to v, or the velocity sine of theta, times the time. Okay, since it goes upward, so we will be using here the negative sign. So that is, we have 1/2 the gravitational acceleration g, then t squared. But since we have this variable v on the equation, so we tried to look for another equation that would give us an equation containing both the variable r and the variable y. So in this case, we will be using the another equation, that is, we have the horizontal distance. We know that distance x is equal to the velocity, initial velocity, times the time, correct? But since here we are referring to the horizontal distance, so we will be using the horizontal component of the initial velocity. That is, we have the x is equal to, now we know that vx equals to v cosine of theta, correct? So this is our vx, then times the time. So we make this equation in terms of x and v, so we express it as t equals to x over v cosine of theta, and that is, we substitute this value to our equation of y. That means we have y is equal to v sine of theta times, we already know the value of t, that is x over v cosine of theta, minus 1/2 g times x over v cosine of theta squared. So we can express it further by canceling the velocity here. So we would have this x sine theta over cosine theta minus 1/2 g times, we have here x squared over v squared cosine squared theta. Now take note, our x here would be the range, correct? So therefore we can say that x is equal to r. So we can change this x here equals to r. Now when we have our x is equal to r at this point here, we can say that our y is equal to 0 because the object is on the ground. So that means when x equal to r, our y equals to 0. So by substituting the value, we would have 0 equals to r sine theta cosine theta minus, we have here 1/2 g r squared over v squared cosine squared theta. But we can cancel r further. We can cancel this r at this point as well. So we would have this sine theta cosine theta equals to 1/2 g r over v squared cosine squared theta. So we can simplify it further by expressing it in terms of theta. So we have r is equal to 2v squared cosine squared theta sine theta over g cosine theta. And we can simplify it by canceling cosine theta here, and we would have this equation of r equals to 2v squared cosine theta sine theta over g. Now take note, this 2v squared over g here is constant. Okay, this is constant because we had given value of v, and we already know the value of g, which is equal to 9.81 meter per second squared. This is the gravitational acceleration. Now take note, we can simplify this cosine theta sine theta here into a single trigonometric identity. Now we have the rule of double angle formula, that is when we have sine 2 theta is equal to 2 sine theta cosine theta. But in this case, since we have only cosine theta sine theta, so we can say that this equals to sine 2 theta over 2. Correct? So we can express this equation into r equals to 2v squared over g times sine 2 theta over 2. So we can cancel out 2 here. So that means our new equation is r is equal to v squared over g sine 2 theta. Again, this v squared over g, this one is constant. Now, in order to compute for the maximum range, we have to apply the maxima and minima concept from our differential calculus, in which in order to compute for the maximum point on the curve, we have to apply differentiation. That means we have to differentiate the point or the variable that we want to maximize. In this case, range is the variable that we intend to maximize. So we derive that in terms or with respect to the other variable. In this case, we have theta. So we have this derivative of the range with respect to the derivative of the angle. But in order to compute for the maximum point, we have to equate this to 0. In this case, we have derivative of the range with respect to the angle. So we derive this one, so we retain the constant v squared over g. So times, so if we derive this sine 2 theta with respect to theta, that means we have cosine of 2 theta, then we derive the angle d 2 theta with respect to theta. So that means we would have 2 cosine of 2 theta. So that means we have 2 cosine of 2 theta. We equate this to 0. So that means we have v squared over g 2 cosine of 2 theta equals to 0. So in order to compute for the theta, so we express this as inverse cosine. So we have 2 theta arc cosine of 0. So we have here 2 theta is equal to 90 degrees. So that means we have theta is equal to 45 degrees. So that means when our range is at maximum, angle is always equal to 45 degrees. So you do not need to derive all of this. You just memorize or familiarize theta equals to 45 degrees when we have a maximum range. So we have our angle of inclination of the velocity that is equal to 45 degrees. Okay, so we can now compute the vertical component and the horizontal component of the initial velocity. So in this case, we have v cosine theta, that is our vx. Okay, so we have 10 cosine of 45 degrees. That would give us 7.071, and the vertical component of the velocity or Vy is equal to 10 sine of 45 degrees, which is equal to, we have 7.071 meters per second. Okay, so it's the unit of the velocity. So the first question is the time the projectile will reach the ground. So basically, we will be computing here the time at which our object is on the ground. So we have our time here, okay, time at this point. So we will use the formula of the vertical displacement, we have y is equal to v times the time plus minus 1/2 gt squared. Now again, our y here is equal to 0 since at this point we do not have vertical displacement. So 0 is equal to v. We will be using here the vertical component of the velocity. That means we will be using here the vy. But since vx and vy are equal, so that means we have the same value of 7.071. Again, this is our vy. Then we multiply it by time t. Then since we have two possible values here, we have positive and negative, but take note, our object is acting against the gravity. Now that's what you can see, the bomb is positioned or directing upward, correct? So that means we will be using here the negative sign. So you have 1/2 times 9.81, that is the value of our g, times t squared. Okay? So in this case, time or the variable t will be cancelled. So we would have this t here cancelled, and then the remaining on the second term is t na lang. So we have this 1/2 times 9.81 t is equal to 7.071. So that means our t here, the value of our time, is equal to 1.442 seconds. Okay? So this is our answer for question number 1. Now for the second question, we are asked to compute for the maximum height reached by the projectile. So the maximum height is at the maximum or the peak of the curvilinear path. So this would be our maximum height. Let's say this is our y max. Now take note, at this point, the object will stop before it goes back to the ground. So that means at that point, the velocity or the vertical velocity or the vertical component of the velocity, vy, is equal to 0. Okay? So we will only have horizontal velocity at that point. So we have here vx. So in this case, we will be using a formula that is the final velocity squared is equal to the initial velocity squared plus minus 2 times the gravitational acceleration times dy. Okay, so this is one of the formula that we need to familiarize in solving kinematics. Since in this case, we are still referring to the vertical distances. So we will be using the vertical component of the velocity. So in this case, we have this v squared, let's say that's our y final, okay, is equal to v squared, we have y initial. This y here indicates a vertical component of the velocity, while f is the final and o is the original or the initial. And since again our object is moving upward, that means we have to use the negative sign. That means the object is acting against the gravitational pull. Then we have a 2 times 9.81. Then our y here, that is the maximum height. That means we have here y maximum. Now we know that at this point, this is our final vertical component of the velocity. That means we have our vyf here is equal to 0. That means we have here 0 is equal to the initial vertical component of the velocity is, from the formula again, we have this 10. We use the sine of angle 45 degrees. We already computed this one, that is equal to 7.071 if you remembered it from our previous problem. Then minus 2 times 9.81 y maximum. So by further evaluation, so we can compute for the maximum y, which is equal to 2.548, and the unit here is in meters. So this is now our answer for question number 2. For the third question, we are asked to compute for the distance traveled by the projectile. So basically, we will be computing here the maximum range. So this one. Now take note, at this point, at the maximum range, the time is 1.442 seconds. So we have this one computed from the first question. Okay? So that means we can compute the range by using the formula. Of course, we have the velocity is equals to distance over time. Since we are referring to the range, so we will be using here the distance. So distance is equal to velocity times the time. So in this case, d is the range, r. The velocity here is the horizontal component of the velocity. So we will be using here vx, then times the time. So we have here r is equal to vx is from the formula 10. Then since the horizontal component is cosine, so we have cosine of the angle 45 degrees times the time. The time here is 1.442 seconds. So therefore, the range is equal to 10.196 meters. So this is now the answer for question number 3. So that ends my discussion in the projectile motion taken from the Civil Engineering Board exam on May 2009. So I hope guys that you have learned something, but please don't forget to subscribe to my channel and hit the notification bell for more board exam problems. Thank you guys for listening, and God bless.